just to give you a background of what we're going to talk about, we're going to talk about how do you solve real-world time series prediction problems. So this is very much in the spirit of the conference. So with this approach, you can actually go and make money on the market. So it will be worthwhile, listening to. So what we do is automated machine learning. So we believe that general artificial intelligence, it's not going to exist in the short to medium term. So in response to this, we're building kind of almost like a narrow AI, realization which solves one particular problem very well. And that problem is prediction, automated prediction algorithms for time series data. So the title of the talk is long, but you'll see what I mean by all parts of that throughout. So just to motivate the talk a little bit, first to talk about where you can find time series data first. So time series data, the obvious place is finance. There's a lot of it there. To think of it as a stock price, macroeconomic variable, anything. You can think of, every server in a server room will produce time series data. Autonomous vehicles produce time series data. If you're Uber or the likes, you have tons of time series data that you can help you predict demand for your services, or, how many people are going to call Uber in the next hour. If you're a commodity trader, you might want to predict, temperatures across regions, which drives, electricity generation. Health data is time series. It's there's a lot of time series data around if you know where you're looking. With the IoT, we will have 50 billion connected devices by 2020. So one report said. So point is, time series data is exponentially growing. So knowledge starts with a definition. So let's first define what we mean by challenging time series problem. That might not look like a challenging problem in context of what we heard about, deep learning and scaling deep learning across multiple servers. But actually, this is super difficult problem to solve, and it's actually very difficult because it's a small data problem. So if you, for example, are predicting, how many cars are going to be manufactured in China, or you're predicting price of Apple. There is some limit to how frequent the data is. So the data that is over there, for example, is at monthly intervals. And you might have a bunch of drivers that are related to this variable. Those drivers might have a very low signal to noise ratio. And you might have a lot of them that have a little bit of signal, each of them. So most importantly, the reason this is very difficult is it's what is called a non-stationary time series. And a non-stationary time series, it means essentially, a complex definition, but in summary, it means that the mean and variance of this thing do not remain constant over time. So the mean and variance change. So this makes it a particularly difficult problem for machine learning. So if you just plug this into a machine learning classifier, you're not going to get very good results. Anyway, so the focus of the talk is how do you solve this complex real-world time series problem? How do you take the stuff on the left, fit it into some box that gives you, accurately predicts the thing on the right? So the answer is actually you need to do a lot of things to get there. We all love deep learning. I love it too, but on 200 data points, it's not going to work very well. Econometricians have been doing this since the 50s. Unfortunately, the techniques are pretty simple, so again, it's not going to work. It's if you like, those are the two kind of ends of the spectrum. We have econometrics, kind of very simple, ARIMA models, all the way to deep learning. So to solve that problem that I show you, you need to be somewhere in the middle. By the way, as a company, we do the full spectrum. So the focus of this talk is just on this particular use case, but in general, we cover the whole spectrum. So to solve this problem, you need to actually use human intelligence, which is not something people talk about on these kind of conferences, but actually it's vital in solving that complex problem we define. Then you need the boring stuff of how do you optimally impute and align the data. And actually, it might seem trivial, and you might kind of pass through it, but it is super important. And I can see someone nodding there that is doing this on daily basis. It's really absolutely vital how you do it. And then, feature extraction. We heard a lot about this. I don't need to repeat myself. All I will say is feature extraction in the context of time series is unique. So special care has to be taken, not to introduce forward-looking biases and all that sort of stuff. Feature set selection, again, everyone in this room knows, why that is important. And, in summary, it's because of curse of dimensionality. More data, more inputs in a low signal-to-noise ratio does not mean better performance. Then we have the notion of, which algorithm do you actually choose? Is it going to be random forest? Is it going to be gradient boosting? Or, what algorithm is going to deliver on this? And then how do you tune the parameters of that algorithm? So that's, if you like, the full pipeline you need to solve in order to solve that challenging time series problem. So I'm just going to show you kind of some experiments we did this morning on the causaLens platform to demonstrate the value of doing all of these steps right. And then we're gonna introduce some cool ideas of how do you put all this together in order to solve this full problem, and you can make some money with it if you get it right. So here it is. The first, let me explain you the experiments we did. So we wanted to prove out the value of doing some of those steps in a constrained environment. So we wanted to introduce only one covariate at a time. So like a proper experiment, proper scientific experiment. So the idea is we keep the algorithm part kind of to the right of the algorithm selection constant, but what we change is the feature selection and the feature extraction process. And we want to see what is the impact of actually doing that properly. So we've run this experiment across a number of data sets, and we measured them across a number of metrics. So what I will show you in the next slide is distributions of those results. So here they are. So first, the value of humans. For these complex problems, and I'm sure if you speak to practitioners in finance, there's a kind of a divide between the guys that believe the machines and the guys that only believe the humans. And we've kind of been showing to the world that really it's about the middle. And this experiment clearly shows that. On the left you have the mean absolute error. On the right you have the Pearson's R between the ground truth and prediction of the experiments. And then on the bottom you have the number of data sets on which we ran this. So what you can see clearly is that introducing a human element into selecting what goes into a model can improve performance by a lot. Yeah, and that's across a large number of different types of data sets. So I didn't want to include and bore you with the statistical tests and all the parameters. I just put one line saying it's statistically significant. But we did t-tests and all sorts of stuff to prove it that those distributions are statistically different. So humans, important on these small data problems. Two, feature extraction. So there's the experiments are using simple feature extraction and using more complex feature extraction. In the time series world, this means, do we just extract one difference and we add the value of the time series, or do we extract more complex features? Do we try to learn, momentum? Do we try to learn mean reversion? Do we take multiple step differences? All these complexities that exist in, for example, financial markets or any actually physical system. So what you'll see that it does pay off actually to extract this time, if you like, from time series. Feeding directly the values of time series will give you the distributions in blue. But if you extract the time element from time series, you get some impressive results. And this is proven across large number of data sets, across large number of model algorithms, and across large number of parameters. So far, human matters, feature extraction matters, especially for time series, because without that, you do not have time from the time series. Second, restricting what goes into an algorithm matters a lot again. And this is especially the case for these small data problems. So what you'll see again that if we have a clever way of selecting features and then feed them into the models, the evidence is there that across large number of models, across large number of data sets, it makes sense to do that. So if you remember, the first slide was about doing a bunch of things in the pipeline, and then we come to which algorithms we select, and then which parameters of each algorithm. What you will find actually, if you try to optimize across this whole space, it's actually a multidimensional discontinuous space. So people call it derivative-free optimization or black box optimization, whatever you want to call it. It's a hard problem to solve in general, but we have done some really cool tricks to solve this problem for the time series world. So we have essentially trained and optimized it to learn how to solve time series problems. So how do you traverse this discontinuous space in which you cannot find gradients in an effective way? And I don't want to bore you. It's Friday afternoon. But we can chat about how you do that. The idea is that doing it properly, it helps a lot. That's your evidence there. So in the first experiment, it was doing everything kind of isolated, one at a time. When you put it together into this full pipeline and then optimizing across this space, also helps the models. So now I want to show you, how I did all these experiments. I ran maybe 6 months of human experimentation time in 15 minutes this morning, and the reason for that is because we have this cool machine which can do this kind of experiment. So you could, given that's here. So this is kind of the data you saw in the presentation, and all I was doing this morning was running cool experiments by clicking this button through the API. And what this was doing you cannot see it. It's a bit strange. Okay. What this button did is essentially ran through all of those steps in the pipeline and optimized it, and then it gave me back kind of the most promising full models. So notice I'm not saying algorithms, I'm saying full models. A full model includes how do you extract features, how do you select features, which algorithm do you select, which parameters do you select, all that stuff. So I just want to show you kind of the winning model from that little discovery process, and you can see essentially that only with kind of 200 data points of this data, we were able to learn a model that solves this very complex time series problem, which is non-stationary, small data, all that stuff. Cool. So I'm just going to leave you now with if I can find my mouse, with one kind of idea that I think it's kind of the future of machine learning in general, is this notion of that real data is dirty, hard to find, and it doesn't let you really push the limits of what's possible with machine learning. So the way we solve that very complex optimization space that is discontinuous and you cannot find gradients is by generating a lot of artificial data. So very, very much like the breakthrough Google had with AlphaGo, is generating data with known properties, adding some noise to it, and teaching your optimizer to learn on a specific problem. In our case, that is time series predictions. So I think, in general, we think that there needs to be more move towards doing this in order to solve, very hard problems in an efficient manner, and the things that work in the real world. So on that note, I will just introduce us. In general, we are early stage startup based in London, and we do one thing, very well, that is time series predictions. And we have attracted some of the world's largest financial institutions as customers because they're very passionate about efficiently solving real world problems with noisy data in situations where they have only a small number of data sets available. But that's my co-founder there, Max. He can tell you even more about all the fun stuff we've done with optimization. So thank you very much. You can have beer now.
Well, coffee and tea first.
Yeah,
beer would be afterwards.
Sorry, yeah.
And after the coffee and tea, there'd be a panel discussion.
All right. Sorry. I was predicting the future wrongly.
No, yeah, it's going to happen at some point, but timescale was different. Any questions for Darko? You guys really need tea and coffee?
Yeah, I think so.
In the demonstration you showed there, where did the human element come in? What do you do?
Right.
You said you pressed the button and it took 15 minutes, but what was the human?
Right. So imagine you're predicting price of Apple. So you could say, hey, I'm going to give the machine everything from all the financial market data. I'm going to take Bloomberg and I'm going to give it to the machine. So that is essentially suboptimal. What the human element was, in this case me, was to say, hey, for this particular prediction problem, I think I have maybe 100 candidates. So rather than having 10 million potential inputs to the model, I restricted the set by knowing what things could potentially have an economic significance in this particular case. If you were doing a problem that is related to demand prediction, for example, you might want to, you're not going to include every single product in the world. You'll say, well, let me think first about what could potentially impact the demand for this product, and I'm going to restrict the space, with using some human intelligence.
A question on your business model.
Yeah.
Is the plan sort of that you're able to generate a higher ROI through providing this as a solution for others rather than using the insights to trade yourself?
Yeah, this is probably the most commonly asked question, and I think there are business models both sides. If you look at the background, we come from some of the world's most famous hedge funds, so we know how to trade. We've been trading for quite some time. I guess it's a strategic question. What is bigger? If we set up a hedge fund, we might attract 10 billion. If we sell this to every company on the planet, the opportunity is bigger. So that's as simple as that, really.
No more questions? 3, 2, 1. Oh, no.
Is the automated part all about the feature selection, or is it the models as well? What gives you the edge?
Yeah, I get. So that gives me feedback that I need to improve my delivery of talk. But yes, it's essentially about the full pipeline. It's about doing everything. Starting from dirty data to an optimal model in a single API call. And I actually didn't show you that bit. That's how you would really use this. Our product is extremely simple. It has one API call for discovery of models and one API call for running models in production. So when you throw this one API call, what it will do all parts of the pipeline, including backtesting and scoring models, and it will give back the best model possible for your problem. And then you can, essentially productize that and have one line of API, one line of code that can run this in production.
How does it? What evaluation metrics is it using? Because you'd want different evaluation metrics
Right.
for different time
Of
series
course.
and different objectives.
That's right. So it's using a plethora of metrics, maybe 20 or 30 at the moment, but you have control over, what is a good model for you. So we typically tend to see people, creating, we call it the causaLens score, which you can actually tune and say, for me, a good model is one that performs, across all these metrics with a given function of your choice. So you can pass a function, which is function of all the possible metrics that we compute, and it's your function, so it will optimize according to that.
Thank you. Follow-up to that question. So do you guys actually provide a predefined way for every step of the pipeline? Or do your customers have some input on the human element of it? And then second part of the question would be, what do you actually use for your optimizers? Thank you.
Right. So we think that what our customers really care about is getting the best possible model. They don't really care how you got there, which is why if you're a portfolio manager, you really just care about predicting what your macroeconomic indicator is going to be. You might not even have any notion of data science at all. You really just want to solve the problem, and that's kind of what the product does. And the second part of the question was?
What do you use for your optimizers?
All right, so we use genetic algorithms, for example, that when you're in a discontinuous space, you have to do that. But there is how we train them. It's kind of where the innovation. So we train them specifically on time series prediction problem with generated data.